Hi and welcome to Foundations 30 with Miss Verity. Today we're going to be looking at 6.3, modeling data with a line of best fit. So a scatter plot compares students' absences from math with a grade that they obtained in the course. So describe the characteristics of a polynomial function that might be used to model the data with a scatter plot. So looking at this data that we've got right here, if we were to draw some sort of graph through it, it could technically be any type of graph. And we would want to go through as many points as possible with equal points on the top and bottom. So if we were to draw, this is going to be an approximate because I don't have a ruler, something like that. Notice it hits lots of points. There's about equal points on the top or bottom. And so based on that trend, it is a line. So we would call that a line of best fit. So a line of best fit is a straight line. And specifically, eventually we'll be talking about different graphs of best fit, but for this section, it's just lines, that best approximates the trend of a scatter plot. The line will go through the dots with approximately half the dots being above the line and half below. A regression function is a line or curve of best fit developed through a statistical analysis of the data. It is the equation of the function that best approximates the data. So we're going to do lines of best fit. There's multiple types of regression functions, and that's essentially these next 3 chapters we're going to be going through. That's all regression functions. Okay, so we are going to be using Desmos. Our Desmos instructions are basically going to be these nice 3 simple steps. You're going to hit the plus button and you're going to select table. You're then going to fill in your data. And then the all-important regression equation that you're going to type in is as follows. Y with a subscript 1, a little squiggle, M, X with a subscript 1, plus B. This is your magic all-knowing equation that you're going to need for this section. Okay, so we've got some data here. So the winning team from the men's 20-kilometer biathlon in the Winter Olympics from 1964 to 2010 is in the table below. So note that the 2004 is excluded. In this table, it skipped a year. So what we're going to say is we've got year 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Technically, year 11 would sit in there. That would be our 2004. So we're going to have 12 and 13. With that, those are going to make up our X values. So then our Y values are going to be everything that's in the table. So it says use technology to create a scatter plot and use the linear regression to determine the equation of the line of best fit. So we're going to go to Desmos. We are going to go to our plus. We are going to go to a table, and this is where we're going to input our data. So year 1 was 80.4. 2 was, I'm just going to go 3, 4, 5, 6, 8, 9, 10. We skipped year 11, 12, and 13. The key thing with this, when you're putting data in, make sure you're putting it in right. If you input or even forget one piece of data or have one typo, you're going to get a wrong equation. So 75.9, 74.2, 68.3. Nope, just kidding. Oh my gosh. 71.9, 56.6, 57.6, 57.4, 56.2, 54.3, and 48.4. Okay, so there's my data, and if you go into your graph, notice there it is. It's all sitting there. So it puts points on the graph. So now we're going to do our regression equation. So we want Y, and hold on, our subscript button is somewhere. So when you go to the ABC, it's the lower one. You want 1. Your side arrow, you want a squiggle. M, we want X. 1 plus B. Okay, and so now notice there's this line that goes through. That is our line of best fit. And on that section, it gives us parameters. It has an M and it has a B. That is actually making up our equation. So if we go back, we know it was in the form of y1 m x1 plus b. When it does this, your ones just mean it's coming from this table, which is an x1 and a y1 table. If you're to put a new table in, you'd have to use, and not delete that one, you'd have to use y2 and x2. So we're going to have an equation y equals the m that our Desmos gave us was negative 2.58016. Negative 2.58016 x, because we're doing it in y equals mx plus b form, plus the b that Desmos gave us was 81.7844. So that is the line of best fit, or our linear regression equation. So determine the possible winning time for the event in the Winter Olympics. So our winning time, that is our y. So that means we are looking for what y is in the 2004 Olympics. So what y is in negative 2.58016. 2004 Olympics was year 11 plus 81.7844. All right, we're going to throw that into our calculator, and we are going to get y equals 53.4, and our units for this is minutes. Compare your estimate to the actual winning time of, well, in that year, it was actually 51. So they were different, and so it was just based on a trend, but in that year, it happened to be a very good year for someone. So our data was slightly off, but that's okay. It's just helping us predict what might happen. Okay, so next we've got interpolation and extrapolation. So interpolation is the process used to estimate a value within the domain of a set of data based on a trend. So if we've got a graph and our data goes from, I guess, like here to here, anything within there would be considered interpolation. Extrapolation is the process used to estimate a value outside the domain. So if we wanted to figure out a value that was way out here, that would be considered extrapolation because it's not within the data we're given. So in the previous example, did you use interpolation or extrapolation? Well, 2004 was within our 1964 to 2002 range, so this would be interpolation. Our next one, a city council needs to buy 15 kiloliters of liquid de-icer for the upcoming winter. One supplier provides the following quote. We are going to have X values, we are going to have Y values. So use the linear regression to determine the equation of the line of best fit. So we're gonna go to our graph. I don't feel like deleting those, so I'm just gonna kind of cover them out. I want a new graph. So notice this one is titled X2 and Y2. So when I do my regression equation, I need to use Y1s or Y2s and X2s. So my points are 9, 10, 11, 12, 13, 14, and 16. So my Y2 values are 1.30, 1.20, 1.15, 1.10, 1.05, 0.95, and 0.84. Oops, let me just fix that one. Okay, so this data is all sitting down here. So now because I had X2s and Y2s, I'm going to go Y to the, ooh, wow, if I could type. Y subscript 2, side arrow, I need a squiggle. I want an M, an X, and a subscript 2, and then plus a B. Okay, so there's my line of best fit. It's given me my M, it's given me my B. I'm going to go back to my notes. So based off of that, y equals negative 0.063811 x plus 1.85914. So what price should the city expect to pay per liter? Currently, we have, everything we have is in kiloliters. So we want to find an x value of x is equal to 15. So we were given in kiloliters and then it was price per liter. So there's two ways of doing this. One of the ways is you can use, like, so I would say y is equal to negative 0.63811, and I would say an x value of 15 plus 1.85914. But we can also use Desmos. Desmos, we want an x value of 15. So we would say x is equal to 15. Well, and that's telling us right there what that y value, what that price would be. So 0.902. So 0.90. And then I guess because it's money, we're going to say just to 2 decimal places. What will the cost of the de-icer be for the city? So that the city's expecting to pay 0.90, and we're saying it's going to be 0.90 for 1 liter. And that is going to be times, there is a total of, we have 15 kiloliters. Well, 15 kiloliters for every 1 kiloliter, we would have 1,000 liters. So that's just like for every 1 kilometer, we'd have 1,000 meters. And so we would have 15, 1, 2, 3. This would be how many liters they would need. So times by 15, equals, this is $13,500. What if the city needed to purchase 20 kiloliters of de-icer? What would their price per liter be? Well, so this is us looking for our cost per liter or our y value. So again, we could say x is equal to 20, and on our graph, x is equal to 20, that's over here. And that is 0.583 or 0.58. Oops, that's not an x. So they would expect to pay 0.58 per liter. That's all I'm going to go through for that one. We are going to go to example 3. Okay. Let's do this one. So Daniela is a real estate agent. She helps businesses move to new offices. If an office does not have enough area, the employees will not be able to work productively. If there's too much area, the business will pay too much rent. So one client has a business with 14 employees. Daniela used the following table about other businesses in one building. So we are going to use linear regression to determine our data. So we're going to go back to our table. Maybe I just want to delete these all now. So my table, I have 4, 6, 10, 12, 20, and 35. 23.2, 36.6, 75.0, or just 75, 79.0, 118, and 245. Oops. Okay, so my points are hanging out there somewhere. There they are. I want my regression equation, so y1 squiggle mx, x1 plus a b, omg, mx plus, there we go. Okay, so there's my m, there's my x. So y equals, this was 6.9474x minus 4.6037. So there are two areas for rent in the building area. Area P has 86 meters and area Q has 100. Which area should Daniela show to her client? So we kind of want to figure out based on the number of people. So our area, that is equal, this number of employees was our X, area was our Y. So if I want to find, so area P is 86 meters squared. So that's 86 is equal to our 6.9474x minus 4.6037. To solve, I'm going to add 4.6037 to both sides. 86 plus 4.6037 is 90.6037. That's equal to 6.9474x. Remember that these numbers are really multiplied, so I'm going to divide. That reduces to be 1. So divided by 6.9474 gives me 13.04. That is what x is equal to. So this area could only hold 13 people. So let's see what the other one can hold. So 100 equals 6.9474 x minus 4.6037. So 100 plus 4.6037. 4.6037 equals 6.9474x. Divide that, 6.9474 is 15.06 is equal to x. So we've got two areas. One, so it basically said, like, if there's not enough area, the employees can't work productively. If there's too much area, then business will pay too much rent. They're either one above or one below. Probably it would be better, I would say, to, I mean, I guess you could use whatever reason you wanted. This one could hold 15 people. This one could hold 13 people. Some might argue that it's better to have a little bit too much room, but they're not paying too much extra because it's only essentially one person more, whereas one person less, there's probably not enough room for people. All right, there you be.